extended to the control of substructures such as the alloy microconstituents or like dendritic structures. And in Foundry practice, the way to modify these structures is this can be done in a couple of ways. Basically, you can vary the cooling rate, you can create agitation during freezing, you can manipulate the superheat, and you can perform chemical treatment of the liquid metal. Now, there's a couple of things to mention here. The first three processes here basically fall under physical techniques and can be explained generally to apply to multiple alloy systems. But the chemical treatment needs to be explained with respect to a specific alloy system because it relates directly to the chemistry of the alloys. So for the scope of this presentation, we will specifically be analyzing chemical treatment with respect to aluminum alloys and cast iron. And another thing to mention is that the terms grain refiner and inoculant are sometimes used interchangeably in the community, but just to avoid confusion for the scope of this presentation, we will use the term grain refiner to specify refinement done in like non-ferrous materials like aluminum, and inoculant will be specifically used for like graphitization of cast iron. So anyway, let's get started with the physical techniques first. So the first thing is cooling rate, right? We generally want fast cooling rate because faster cooling rate will suppress the growth suppress like columnar growths and will basically reduce the critical radius of nucleation, which means there will be more places where nucleation will occur. So you will have equiaxed grain structures compared to slow cooling rate, where with higher critical radius of like stable nuclei, there will be less nucleation zones. Therefore, you will have larger grain structures. Now, generally, in terms of the cooling rate, the choice of cooling rate will largely depend on the choice of the solidification method being utilized. So there are different types of solidification methods that can be used, and depending on that, the cooling rate will vary. Secondly, there's lots of factors that affect cooling rate, like for example, if we vary the mold material with metal mold, there will be higher cooling rates. If we use chill, we will get excellent grain refinement because of the very high rate of localized heat transfer. If we have high pouring temperature, generally like the grain refining will be bad because the cooling rate will be bad, and this is because the mold will be preheated at higher pouring temperatures. At lower pouring temperatures, we will get better grain refinement. Now, another thing to recognize here is that in case of using chill, the chill should be placed far away from separation zone, which is the mold surface from which the columnar grains tend to separate. Because if chill is placed there, it can actually promote the growth of columnar grains and therefore suppress the equiaxed crystals. Now, one thing to note is while there are different types of variables that we can control in practice, a lot of these variables are actually placed into narrow limits because of foundry requirements such as fluidity and feeding. So a lot of the times, like the use of mold or the use of chill or even the pouring temperature will be predefined based on other design requirements, and we won't be able to control these as much as we would want to. Superheat, generally, we want to have low superheats if we want to have equiaxed structures. This is because we don't want the separated crystals to remelt when they enter the center of the solution. But there is a balance to be made. So we want the superheat to be low as possible so that enough crystal separation can happen without remelting. But the superheat needs to at least be at a level such that there is enough thermal convection that allows grain separation to happen. So that's sort of the optimally low superheat that we are going for. So now this is just a like a mentioning a process that actually utilizes superheat, the principle of superheat to achieve equiaxed dendritic formation. So equiaxed grain formation. So the name of the process is low superheat casting, or LSC process, which basically solidifies the alloy just above the liquidus temperature. As a result, it triggers equiaxed formation by suppressing dendrites. The other process that we can use in terms of physically refining is agitation, where we can mechanically agitate the system to, one, distribute the nuclei so that the nuclei is more evenly distributed, but secondly, to fragment the growing columnar or dendritic crystals and prevent them from growing in a columnar fashion. So agitation can be done mechanically, but it can also be done in other ways, like in case of ultrasonic treatment or electromagnetic stirring. So in ultrasonic treatment, there will be an ultrasonic generator that is used to generate ultrasonic waves within the melt, and these like ultrasonic waves will basically vibrate the melt and cause the agitation. In electromagnetic stirring, magnets basically can be used to induce convection currents within liquid metals and thereby promote grain separation and further equiaxed grain formation. And this is basically a schematic of how ultrasonic generators are applied in practice. Now we'll now move into the chemical refinement, and we'll start by talking about the refinement of aluminum alloy using grain refiners. Aluminum is going to be the sort of a representative of other non-ferrous alloys. So firstly, to mention that grain refining is incredibly essential in case of aluminum alloy production, because if you look at this, these two are situations where we didn't add grain refiner to the system, so we get a very large fraction of columnar grains with very bad anisotropic properties, whereas here we added a lot, like the proper amount of grain refiner, achieved almost complete equiaxed grain structures, which have superior mechanical properties. So the normal grain refiners that we add to aluminum are basically titanium and boron. And the goal here is to form this equiaxed alpha aluminum phase, which is basically solvent aluminum with little amounts of like titanium boride dissolved in it. And basically, the way we use a grain refiner is it's based upon this master alloy system of aluminum, titanium, and boron, which contains particles of titanium boride and aluminum and titanium aluminide in the alpha aluminum matrix. And the reason we need this basically is these materials are basically the nucleation sites for the growth of the aluminum grains. And this is something that has been detected by experimentation, where we've actually found these particles at the center of aluminum grains. So this can be understood in a couple of steps. So first of all, we can look at the effect of aluminum, like a titanium addition to aluminum. So basically what titanium does is it promotes the formation of that alpha aluminum. So when you have very low concentrations of titanium, then in the casting temperature, the entire melt will basically be in the liquid phase, but increasing the concentration of titanium slightly will promote the formation of this alpha of this alpha phase as we cool the structure. And basically what happens is that this alpha phase will nucleate on top of this aluminum titanium particle. Additionally, when we add boron, they basically undergo this eutectic reaction that produces that alpha aluminum solution as well. Now the combined effect can be seen from this graph, where when you add both of them, essentially what happens is firstly the titanium bromide crystals like bromide crystals grow, and then on top of them the the titanium aluminide gets adsorbed, and this basically forms the stable nucleus upon which the aluminum grains can start to grow more frequently. And the ratio of titanium at which these happen is basically at 0.15 weight%, which is why you have this transition here. So in this graph we see the number of grains per volume, which means at lower values you have larger grains, at higher values you have smaller grain sizes. So you have a transition to much smaller grain sizes once you increase the amount of titanium, such that this type of nucleating species are present within the melt. But it's not just enough to ensure that you have nucleating species. You also need to be able to suppress the growth such that more nucleuses can form before any other nucleus or any other like column dominates in terms of the growth. So So in Campbell, they basically devised this restriction parameter called Q is equal to mk minus 1 C naught, where K is the partition coefficient, C naught is the average solute content at the separation front, and M is the slope of the liquidus. And basically this is used as a measure to quantify the extent to which the growth is restricted. And there are different values of this for different types of solutes that you can add as grain refiners. But one thing to notice here is that generally, the effect of this restriction is positive in a very small range, right? So generally, when we increase the percentage of certain types of solutes, the grain size decreases rapidly. But beyond this point, in trying to increase this parameter Q actually leads to an increase again, or a rise of the grain size, which means for this type of system, there's a minimal limit of like the grain size reduction that can be achieved by adding these solutes, and beyond which basically there's a poisoning effect of grain refinement. So the way they explained this is that they said that, so for example, most of these alloys here on this part of the curve are ones where we have silicon additions on top of like titanium as well. And when we increase the amounts of silicon within the melt, it tends to poison the grain refining action of titanium. Okay. Now, one other thing to mention, which is interesting for aluminum, is aluminum, because it's a readily oxidizable metal, actually forms bifilms, and these bifilms can be very harmful because they can form, they can form cracks and nucleate porosities and whatnot. But when we add grain refiners into the solution, these refiners actually grow on top of these bifilms. They make them heavy, and this causes the sedimentation of these bifilms onto the bottom of the casting, thereby removing it from the interior of the casting. This can, therefore, the grain refinement not only produces like equiaxed grains, but it also basically improves the cleanliness of the melt. But this is also sort of a double-edged sword, because if we additionally do studding for grain refinement, then a lot of these heavy sedimented like bifilms with the grain refiners deposited on top of them, they can get reintroduced into the casting and impair the properties. So if we do use grain refiners to create clean melts, we have to be very aware of how we start that melt. Finally, for the dendritic arm spacing, there's a bit of an indirect relationship when it comes to aluminum alloys, which is that the presence of the bifilms within the melt actually reduces the thermal conductivity and therefore reduces the heat extraction from the melt. But when we add these grain refiners, they basically sediment the bifilms and they increase the thermal conductivity, thereby more heat is extracted, which reduces the dendritic arm spacing. And we know that lower dendritic arm spacing gives us better UTS, better elongation, and whatnot. Now let's move on into the inoculation of cast iron. So basically, inoculation is the treatment of cast irons by deliberate addition of particular materials to control the type and distribution of the graphite formed. And the aim here is to exert control on the graphite flake morphology and to basically get better mechanical properties. So when we say type, we mean, do you want flake or do you want nodular or like spheroidal graphite flakes? And when we say distribution, we're talking about achieving a uniform distribution where the sizes are uniformly distributed as well. So let's talk about the inoculants first. The widely used inoculants are ferrosilicon, calcium silicide, and graphite. This is lump ferrosilicon powder, powder ferrosilicon. This is calcium silicide and graphite lumps. And generally, ferrosilicon is known as a clean inoculant, whereas calcium silicide is known as a dirty inoculant. And the reason is when calcium silicide enters into the melt, it reacts with air to form calcium oxide surface films that basically, if you have a turbulent filling system, it can become folded and again produce harmful bifilm inclusions, which means in order to effectively use calcium silicide as an inoculant without harming your casting, you will need to use it in conjunction with filling systems that are designed to minimize turbulence. The other question is that even though we say that ferrosilicon is sort of the primary inoculant, it's never really chemically pure because it's never viable to make these completely free of impurities commercially. And on top of that, certain deliberate additions like magnesium, calcium, strontium, etc., are added because these can form complex oxides and oxysulfides, which act as heterogeneous, like solid heterogeneous nuclei for graphite formation. So here's just some examples of commercial inoculants. And these are grades, and basically what you can see here is that even though the main element is the ferroalloy, the main product, like the main substance is the ferroalloy with silicon, there's also other varying amounts of other elements added to it. Now we'll talk about the mechanism of inoculation. So in terms of the solid microinclusions, which is the sulfides and like the oxysulfides and the complex oxides that are formed, the mechanism is relatively straightforward. Basically, the presence of these inclusions within the melt provides suitable surfaces and crystallographic characteristics which are favorable for the heterogeneous nucleation of the graphite. However, the most prominent inoculant that we use for this system, which is ferrosilicon, if you look at the melting temperature, it's actually liquid at the casting temperatures of liquid iron, which means that ferrosilicon can't really be a solid heterogeneous like nucleation site for graphite. So what's happening here? Basically, what happens is ferrosilicon melts, but it continues to exist as a region of high silicon concentration within the liquid melt for a period of time. So even though these two liquids are completely immiscible in one another, they take some time and interdiffuse before silicon dissipates completely into the melt. Now, during this temporary region where you have a silicon rich region within the melt, during this temporary region, this actually increases the carbon equivalent solution locally. So let's say we have a 3% cast iron, in which case we would have a carbon for 75% silicon, we would have a local carbon equivalent number of 28%. And so Campbell and his colleagues basically predicted that, okay, if you have 28% carbon equivalence, then you can take an iron carbon diagram and you can basically extrapolate this liquidus line. And if you extrapolate it to this like unnaturally high amount of 28% carbon, we can predict a very high liquidus temperature of an up to like a couple thousand degrees. So what they essentially argue from this is that within this localized region, the graphite is basically artificially, in an artificial manner, tremendously undergoing constitutional undercooling. So basically they framed it as artificial constitutional undercooling for the duration of which the silicon content within that region remains high. So in that localized region, the tendency or the driving force for graphite precipitation increases, and as a result, we get we get the nucleation of graphite. But as soon as, just like solid inoculants, once solid inoculants dissolves, the effect of the inoculant fades away. Similar to that, as the silicon region dissipates into the liquid, it also fades away just like any other inoculant. Now, there are basically two major methods of how to add these inoculants into the melt. There's ladle inoculation and late inoculation. For ladle inoculation, we basically put the inoculants either as the liquid metal is entering into the ladle, and this might be from a furnace into the ladle, or it might be from another ladle into the current ladle. And this can be done in different mechanisms like gravity feeding, air assisted injection, or cored wire methods. So for gravity feeding, the hopper is just placed above and the action of gravity feeds the inoculant into the stream. Air inoculation uses air blow, and the cored wire method we can talk about in a little bit more detail. So basically in the cored wire process, you have inoculants that are added in the form of a core of a hollow mild steel wire. So they're put inside the hollow, like the inoculant powder is put inside the hollow wire. And basically the wires are fed by an IMREX treatment station, which consists of a coil, and this coil is then directed through a guide tube into the close fitted lid of the ladle. And inside, the sheath of the steel dissolves, basically releasing the inoculants into the melt. Now, late inoculation, however, refers afterwards. So if you basically treat the inoculation into the stream after it has left the ladle, or it has entered the mold, then we call it late inoculation. So there are different types of late inoculation, like in-stream inoculation, wire inoculation, and in the mold inoculation. So this is an example of in-stream inoculation. It's very similar to the previous one, where you have a hopper, a dispenser that dispenses the inoculation into the stream. But here, instead of going from furnace to ladle, we are going from ladle to mold, and just as it enters the mold, this stream is being provided. Now, there's a couple of criteria that needs to change. The inoculation must be more powerful, simply because it has to act faster, because there's less time before the solidification process starts. Secondly, it must be finely divided to ensure free-flowing properties and rapid dissolution. It cannot take too much time to dissolve. And thirdly, it must also be very well graded. If the distribution is too fine, then during this blowing process, they simply might blow away and we can lose a lot of inoculant. And if they're too large, then they can jam this system. The other way of doing this is mold inoculation. This is another type of late inoculation. In fact, it takes place much later than in-stream inoculation, which is that you can place either powdered inoculant or a precast slug of solid inoculant within the running system. So it can be placed within the sprue basin. It can be placed on the sprue base. It can also be placed along the runner. And as you pour the metal, as long as you can ensure that it's positioned in a place where there is adequate motion of moving hot liquid, these inoculants will dissolve and they will start their inoculation action just as solidification starts to happen. This is very good because it basically minimizes or oftentimes diminishes the fading of inoculants, because the inoculants go into effect and just as the inoculants start to fade, the solidification process begins. Whereas in ladle inoculation, the inoculants might have faded, the effect of inoculants might even fade way before the solidification even starts. So this also has another additional benefit, which is that we would require lesser amount of inoculant in comparison when we use mold inoculation or late stream inoculation, simply because we would not have to compensate for the inoculant that would fade over the waiting period for processes like ladle inoculation. Okay, like the final thing that we want to mention in terms of the foundry practice for adding inoculations is there's some special consideration that needs to be made when adding it to ductile iron. So we know that in ductile iron, magnesium is added to assist in the spheroidizing of graphite particles. However, what's important is that magnesium is also a very strong carbide former. So even though when we want to produce graphite, we are trying to suppress carbides, the presence of magnesium can actually promote the formation of carbides, which means that the need for inoculation for ductile iron is actually even more than gray cast iron. So how do we add this inoculation? Well, one of the tricky things about ductile iron processing is that when we pour the molten iron into the ladle, the treatment alloy, the magnesium MgFeSi alloy, is already placed within the ladle. And this magnesium has a very high vapor pressure and low melting temperature, which means the reaction is very vigorous and a lot of magnesium is lost in the form of vapor. So this is called magnesium flare. During practice, it's very important to recognize that this magnesium flare can be ineffective, it can make the inoculation addition ineffective. So what is generally practiced is that, first of all, the metal is tapped in, and the magnesium flare is allowed to first subside, and then the remaining metal is tapped in, and with that metal, the inoculation is added so that the inoculation can begin after the initial vigorous reaction of magnesium has already subsided. So these are the references that we used. Thank you.
Okay, please close it. তোমাদের কি inoculation and grain refining. Okay. কোথায় গেল? ঠিক আছে, কিছু বলার নেই। Next group আসে roll number 27, 28, 29, 49. আচ্ছা তোমরা সবাই?
Yes sir, 27.